There is a star 8,000 light-years from Earth that is going to explode. And in 2008, astronomers measured the direction it would shoot in. It pointed roughly toward us. The star is called WR104. It sits in the constellation Sagittarius, deep enough into the disk of our galaxy that most amateur telescopes never resolve it. What you would see, even with a small instrument, is a single bright point. But that point is not one star. It is two. WR104 is a binary system. One of the two stars is a Wolf-Rayet, a class of massive dying star that has burned through its hydrogen envelope and is now burning helium directly. Wolf-Rayet stars are rare. They live fast and die violently. Less than 1,000 of them are known in the entire Milky Way. The other component of WR104 is a younger, hotter main sequence star called an OB star. The two orbit each other every 240 days, roughly.
When the wind from each star slams into the other, dust is created. Not the kind of dust you find on a table. Dust made of carbon, condensed out of stellar plasma at temperatures and pressures that no laboratory on Earth can reproduce. And because the two stars are orbiting, that dust gets ejected in a spiral. From 8,000 light-years away, the spiral is too faint to see in visible light. But in 1999, Peter Tuthill, an astronomer working with the Keck telescope's infrared interferometer, resolved it. The image he produced is one of the most striking direct photographs ever taken of an exotic stellar system. A perfect rotating spiral of glowing dust expanding outward, like cream stirred into coffee, except the coffee is interstellar space and the cream is plasma. They named it the Pinwheel. And from the geometry of the pinwheel, its precise opening angle, its rotation direction, the way it expanded, you can deduce something specific. You can deduce the orientation of the orbital plane of WR104.
Because the dust spiral is created perpendicular to the orbital angular momentum, the plane of the pinwheel is the plane of the orbit. And in a Wolf-Rayet binary about to explode, the orbital plane is often, but not always, aligned with the rotational axis of the Wolf-Rayet star itself. That matters, because when a Wolf-Rayet star dies, it does not just explode outward. Sometimes, under the right conditions, with enough rotation, with the right binary interaction, it can produce something far narrower than a supernova: a long-duration gamma-ray burst.
A gamma-ray burst is the most violent event known in the modern universe. For a few seconds, sometimes minutes, a single point in space can outshine every other star in its galaxy combined. The energy released is comparable, in those seconds, to the entire output of the Sun across its 10 billion-year lifetime. But here is the part that matters. A long gamma-ray burst does not radiate equally in every direction. The collapsing core of a rapidly rotating massive star produces two narrow jets, opposing beams of relativistic plasma, drilling out along the rotational axis. The opening angle of each beam is typically only a few degrees. If you are outside the beam, you see almost nothing. A distant flash in the infrared days later, maybe a faint radio signal. If you are inside the beam, the burst hits you with the full energy. For a target like Earth, that distinction is the difference between an interesting astronomical event and an extinction.
The lethal range of a long gamma-ray burst is debated. Most models put serious atmospheric damage, destruction of the ozone layer, mass extinction of marine and surface life, at distances out to roughly 6,000 to 8,000 light-years.
A nearby gamma-ray burst has been seriously proposed as a trigger for the Ordovician mass extinction 440 million years ago. It is one hypothesis among several. The evidence is indirect, but it is taken seriously. WR104 is at the outer edge of that lethal range. It is also, almost certainly, going to produce a supernova. Wolf-Rayet stars in WR104's class were born somewhere between 25 and 40 solar masses, though by the time they reach this stage, violent stellar winds have stripped much of that material away. What remains collapses to form either a black hole or, in extreme cases, a magnetar when the core fuel runs out.
What is not certain is whether that collapse produces a gamma-ray burst. The conditions are demanding. The star needs to be rotating rapidly. The binary companion may need to play a role in stripping the envelope. And the jet has to break out of the surrounding material cleanly. In 2008, Peter Tuthill and his collaborators combined the pinwheel geometry with what was known about the rotation axis. They concluded that the axis was tilted approximately 12 degrees from the line of sight to Earth. For a beam with a typical opening angle of a few degrees, that is outside the strict danger zone. But for beams at the wider end of the observed distribution, 12 degrees is, quote, uncomfortably close. That was the headline. WR104, the gun pointed at Earth.
The 2008 paper was not the end of the story. In the years after, more measurements came in. The pinwheel was re-imaged with higher precision interferometry. The orbital parameters were tightened. New groups used different methods. And what they found was not a confirmation. It was a complication. Some analyses pushed the inferred tilt of the system wider, closer to 30, even 40 degrees from our line of sight. That is outside the typical opening angle of a long gamma-ray burst jet by a wide margin. But wider is the right word, not safe. The new measurements disagree with each other. The system geometry of a binary at 8,000 light-years, half hidden in dust, is brutally hard to pin down. And the deeper you look, the more reasons there are to keep the file open. The first is the measurement itself. Different teams using different telescopes get values that disagree by enough to matter. The 2008 number is no longer the consensus. There is no consensus.
The second is the beam. Not every long gamma-ray burst has a narrow jet. Some have wider opening angles. Some are powered by mechanisms astronomers still do not fully understand. The catalog of well-studied long bursts is only a few hundred events. Sample size matters when you are trying to predict an outlier. The third is the dust itself. WR104 sits in a star-forming region of the galaxy, thick with other massive systems. Wolf-Rayet binaries with similar geometry exist elsewhere. Some are cataloged. Some are still hidden behind exactly the kind of dust WR104 produces. The galaxy contains, by current estimates, a few thousand massive stars in the late stages of their lives. Most will explode quietly as ordinary supernovae. A small fraction will produce gamma-ray bursts. A smaller fraction still will have those bursts aimed in our direction. The probability that one is aimed at us right now, in any given 1,000-year window, is small. The probability that one has been aimed at us, somewhere in the 4.5 billion-year history of the planet, is much harder to argue against. WR104 is the one we found.
WR104 will explode. That much is fixed. When it does, the explosion will be visible from Earth, possibly during the day, brighter than any other star in the sky, for weeks. The light that announces it will have left the star 8,000 years before any of us were born to see it. If the rotational axis turns out to be more aligned than current measurements suggest, that light will be followed by something else. A gamma-ray pulse, lasting seconds. Ozone destruction. A photochemical cascade that nobody alive today would survive in its full form. If the axis is misaligned, as the current best estimates suggest, the burst will pass us by. We will see a beautiful new supernova and write papers about it for 50 years. The honest answer is that we will not know which one until the explosion happens. WR104 might detonate tonight. It might wait 300,000 years. There is no precursor signal we can monitor. We are simply in line with a gun, probably outside the cone. Probably.
Next video. The largest gravitational anomaly in the observable universe sits about 220 million light-years away, and our entire galaxy, along with half the local supercluster, is falling into it.